So now we move on to multiplication with fractions. And I think this is a really important place to start. It's just going back to the meaning of multiplication. You can see here, given a product of two whole numbers, we'll call them m and n. We can think of the first number, m, as indicating how many we have of the second number. So when we see 2 times 3, what that really means is we have two threes. 3 and 3, maybe we consider them even added together, is 6, right? The first number is telling us how many of the second number we have. So let's take that thought into fractions as well. If we write 1/3 times 6, that also really means 1/3 of 6. That's an important thing to recognize. And so if we take that into consideration, a model, a visual, let me redo that. A visual would look something like this, shown with these dots here. So again, we have the 6 dots, and we're taking 1/3 of them, right? Here are 3 groups, each with 2 in them, and we're taking one of those groups. So this is showing 1/3 of 6. So we're going to start multiplying fractions by some whole numbers. But there's a really funny thing that happens that can often be a little confusing. When we multiply by a whole number greater than 1, the product is greater than the second number being multiplied. But when we multiply by a fraction less than 1, the product is less than the second number being multiplied. And that's often a bit tricky for school children to recognize because they tend to think about when you multiply two numbers, the answer is bigger. But when you're multiplying by a number less than 1, a proper fraction, that doesn't happen. And so we really have to build in that modeling, right? So if we start by interpreting multiplication as repeated addition, like I demonstrated here with the 3s, then that can be a good place to start. And so I'm going to start by showing you what 3 times 2/5 might look like in an image. And that is going to look like this. So if we start with one whole bar and we break it up into 2/5, so here's 1/5, here's 2/5, so there's 2/5 right there. But then we take that amount 3 times. So here we have it once, here we have it twice, and here we have it 3 times. So this shows 3 of those 2/5. And then we look at what the total length is, right? So the total length from the beginning here to the end, which is here, how far does that span? Well, this is one whole bar from here to here. And notice that we also have an additional one piece, 1/6. So it's a total of 1, 2, 3, 4, 5, 6 fifths. Fifths, we're counting fifths. Plus it is again a total of 6 fifths, 1, 2, 3, 4, 5, 6, which is one whole bar plus an additional 1/5. Right? So that model right there shows that idea of repeated addition. Well, what if we look at the fraction times a whole number in the other way around? 1/3 times 4 means 1/3 of 4. Those are equivalent statements. And so this product can be illustrated if we use 4 whole bars and divide the entire set into 3 equal parts. So this is how many things we have, and this is how much of that we are going to be using. And so it might look something like this. So we've got 4 bars, right? 1, 1, 2, 3, and 4. And then we're going to draw vertical lines cutting those into 3 sections, right? So how much do we have then? Well, if we look at these, those are all thirds, right? This is a third, third, a third, which means we have 4 of these thirds, which can also be stated as 1 and 1/3. So again, here's another way to model that idea. We start with 4 full bars and we cut the whole group into 3 pieces so we can just take away and look at a third of them. Here's one more way to examine that same problem of 1/3 times 4, and it's to do this. It's important to have all of these tools at our disposal, all of these different ways to think about it. And so we can illustrate it with the 4 bars lined end to end, right? 1, 2, 3, 4. So that's those 4 bars. And then we're dividing this length into 3 equal pieces. So we have to cut it into thirds. And then we look up, well, how big is that? How big is that? So if we put our yellow bar underneath, which is cut up into thirds, we see we've got 1/3, 2/3, 3/3 to make one whole, and then a 4th third, or 1 and 1/3, right? So we can see this is just a different way to analyze that same problem. A different way to analyze that same problem. And so here is a way that we can define this algebraically, like we always do. And once I go through this, I'm going to go back and look at that previous example that we just did. So this says for any whole number k and fraction a over b, k times a over b is equal to ka over b. Notice how the whole number just gets multiplied by that numerator. Same thing if it's written the other way. A over b times k is equal to ak over b. These get multiplied, but the b just comes along. Didn't we see that same thing up here? 1/3 times 4, the 1 and the 4 got multiplied, and we ended up with 4 over 3. Same thing if we multiplied 3 times 2/5. We multiplied the 3 times the 2 to get 6 over 5. And maybe now you can connect that idea to what we actually did in that diagram. So now let's have you try a couple. Let's try multiplying 3 times 2/7 and this one, 6 times 3/8, and be sure to write your answer in simplest form as well. So if we use what we just learned, a whole number times a fraction, the whole number just gets multiplied by the numerator. 3 times 2 is 6 over 7. On this one, 6 times 3 is 18 over 8. But that can be simplified in a number of ways. If we reduce it, we can divide a greatest common factor of 2 out of both of those numbers to get 9/4. And then we can change that to our mixed number. 4 times 2 is 8, plus 1 gives us 9. 2 and 1/4. So just to, again, take a look at one of the content standards for grade 5. This is what we're going to do next. So we're going to start looking at multiplication of fractions using some area models, areas of rectangles to demonstrate. This is one of the expected grade 5 standards that students will be able to do what we're about to look at right now. So it's not just about calculating the multiplication of fractions. It's about being able to represent them visually as well. So let's take a look at the problem, the product, 1/3 times 1/5. Again, remember this also means 1/3 of 1/5. It's important to have that little distinction there. And so a way that we can model this, I'm going to just draw this one out. If we think about this as our starting point, sketch a rectangle and cut it into 5 equal vertical pieces like that. So there, our rectangle is cut up into fifths, and we're going to use just one of them. So I'm going to shade in just one of my fifths. Okay, so this section is representing 1/5. And now what we're going to do is we're going to take 1/3 of this. So I'm going to now draw horizontal lines to cut my entire rectangle into thirds. And then if we just look at this bottom one, we say this distance from here to here is 1/3. This distance from here to here is 1/5. And so the overlapping section, if we even consider this entire thing, the overlapping section is here. That's the area that we are looking at. And if we compare this little corner to the entire rectangle, how many pieces does our rectangle have now? 5 times 3. And how many of them are shaded? Just that one right there. So we can see from this model that 1/3 times 1/5 is equal to 1 out of 15. That's this representation of an area model. But we can also do this another way. We can look at this same problem another way, not like that, but like this. So if we draw a rectangle, again, that's the one in the background from here to here, and we shade in one section of it. This right here represents 1/5, that little section down there. And then we're going to take 1/3 of it, which means we're going to cut that into 3 pieces, and we can do it like this as well. We can make vertical lines. But just to make sure we know what our correct denominator is, we would then do it all the way across. Every piece would get cut into thirds. And if we look at it, we then can see that there are 15 of these vertical bars, and we are only going to take one of them right here, because we're taking 1/3 of this 1/5. 1/3 of this 1/5 is 1 out of 15 total slices. So we can also view it like that as well. So let's look at this one now, because those were fractions where we had a 1 in the numerator. Let's see if we can figure out what 2/3 times 4/5 looks like. And remember, that also means 2/3 of 4/5. Maybe you try to sketch out what you think a rectangular model would look like. Did you come up with something that looked like this? Let's examine this drawing. If we start with 4/5, draw your rectangle, and then we count 1, 2, 3, 4, 5 sections. You can see 5 vertical sections. 4 of them are shaded in. So this section, this section, this section, and this section represent 4/5 of the original rectangle. Then we're going to take 2/3 of that section. So we're going to cut horizontally into thirds. And we're going to count 2 of those now. So we're going to here to here and here to here. And we're just going to look at then this section that's boxed in right there. Where do those 2 overlap? Well, how many pieces do we have now? It's 5 by 3, so it's got 15 total pieces. But we have 2 times 4 that are shaded that dark red on the inside. So that gives us 8/15. Just like before, we can also represent this same problem using a single bar. You don't need to see the whole thing. Let's make it a little simpler for you here. We can just look at this. And so again, if we start with one long rectangle and we cut it into 5 pieces, that's what we see here. And we're going to shade 4 of them. So there's our 4/5. This section down here on the bottom, all the purple. But then we're going to take 2/3 of those 4/5. So again, cut every piece up into thirds, 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 all the way across. And then we are going to take 2/3 of them. So in each of these rectangles, we're going to take 2/3 of you and 2/3 of you. And you can see these darker shaded purple sections here and here, here and here, here and here, and here and here. And then we count them. We've got 8 total dark purple shaded in rectangles. 8 out of those entire 15 are shaded. So again, a couple different ways to look at those multiplication of fractions. If you've been paying attention, what you may have noticed is that with all of these, what we end up doing is just multiplying the denominators together and multiplying the numerators together. 2 times 4 is 8, 3 times 5 is 15. Every single time. That's how we define multiplication of fractions. But we have to start with the visual models first before this makes sense to us. So again, for any fractions a over b and c over d, we are just multiplying the numerators, and then we multiply the denominators. Now, it is important to say that you can get mixed numbers in these cases, and we always want to make sure that we, if we are multiplying a fraction by a mixed number, then we want to make sure our fraction looks like a fraction, right? We want to change our mixed number into an improper fraction. And so that is an important note as well. So let's just try a couple of these fraction multiplication problems. Let's do 1/2 times 8/9, and let's try 4/7 times -2/5. Go ahead and pause and try both of those. So let's check. We just learned we are multiplying numerators and numerators and denominators and denominators. So this one would be 8 over 18, and we can reduce that by dividing out a common factor of 2 to get 4/9. On this one, we get a negative number. 4 times -2 is -8. 7 times 5 is 35, and that's it. That's all we can do with that one. Let's see what some of those mixed number multiplication problems would look like. Let's try 3/4 times 6 1/5. So in this one, I'll do this one, and then I'll have you do one on your own. 3/4 is already a fraction. It looks like a fraction. But we need 6 1/5 to look like a fraction. So we'll do 5 times 6 plus 1, which is 31 over 5. And then we can do our multiplication. 3 times 31 is 93. 4 times 5 is 20. With a little division or counting by 20s, we see that 20 goes into 93 4 times, which gets us to 80. And then that leaves us 13 more to get up to 93. 4 and 13/20. So now that you've seen one, go ahead and try this. 3 1/8 times -2 1/3. Give that one a shot. I'll go ahead and work it now. 8 times 3 is 24, plus 1 is 25 over 8 times. Same thing here. Remember, just ignore the negative. 3 times 2 is 6, plus 1 is 7/3, and then go ahead and put that negative back in. 25 times 7 across the top is 175. It's going to be negative, and 8 times 3 is 24. And if we do some division there, 24 goes into 175 7 whole times with 7 left over, 7/24, and that is going to be negative as well. That might require a little long division, or there might be some methods you can use to do that in your head. So now let's move into talking about division. Division of fractions can be viewed in much the same way as division of whole numbers. When we looked at division back in that whole number section, one of the meanings was the subtractive concept, which meant that when we were dividing something like 15 by 3, we thought about it as how many times can we subtract 3 from 15? The 3 told us the number in each group. And the quotient, the answer to that of 5, that told us the number of groups. So if we just keep taking 3 away from 15, 3, 3, 3, there's a group, 3, 3, 3, there's another group, 3, 3, 3, there's another group, 3, 3, 3, there's another group, 3, 3, 3. We've exhausted our 15, and we come up with 1, 2, 3, 4, 5 groups. That's how we view that measurement or subtractive concept. We can do the same thing with fractions. We can take 3/5 and divide it by 1/10, which means if we start with 3/5, how many tenths can we take away from it, right? How many groups would have a tenth in it? And so that might not be entirely obvious to you visually until we look at something like this. Let's examine this. So here you will notice the top bar represents 3/5. 5 sections, and we have 1, 2, 3/5. And the bottom we have cut up into tenths, and here's 1/10. So this is a tenth, and this whole thing up here represents 3/5. And so if we imagine taking away 1/10, that would be taking away one section here. I'll tally them over here on the left. And then we take another tenth away right here. There's another one. Take away another here. Another here. We're up to 4. Another here. 5. And another here. 6. We can use that subtractive principle to see that 3/5 divided by 10 is equal to 6. 1/10 fits into 3/5 6 times. Now, that's a visual. That's one visual that can help us see this, this representation. What we'll look at now is another situation, another problem. And this one is going to be 5/6 divided by 1/3. And so maybe you even try to sketch out a bar like we did in the previous example. See if you can maybe represent this like we did here. See what yours might look like. This is often a challenging process when you're first learning this. It just takes a lot of sitting and staring and thinking about these for it to really start to sink in. And so this top bar represents 5/6. We can see that right here, 5 out of 6. The bottom bar is 1/3 right here. So again, we're trying to figure out how many of these we can take out of here. Well, here's 1, here's 2, but then we still have this remainder over here. And if you compare the remainder to the divisor of 1/3, you see that this is half of this. So we end up with an extra half, or 2.5, because sometimes it doesn't divide in evenly. So that's, again, how you can visualize fractions. Now, what you're probably thinking is, I've learned to just multiply by the reciprocal. Maybe that's a phrase that sounds familiar to you. So we're going to get there, because that's a common way that fraction division is taught now. But just so you know some history, one of the early methods, we don't really teach this method much anymore, but one of the early methods said, get common denominators with your division. I know we don't do that anymore, but one of the earlier methods said to do that. If we did that, it would look like this. And then once you get your common denominators, you just ignore them and take the numerator, 8 divided by 15, which is 8/15. And that way, it does work. What we tend to do now, though, is multiply by the reciprocal. 2/5 times, when we invert the divisor, it has this name. It's called the reciprocal, 4/3. And then it's a multiplication problem. 2 times 4 is 8. 5 times 3 is 15. Notice we got the same thing here as we did here. So again, a couple different ways to examine that. What we're going to do in these next few minutes is examine why that is and why that method does work. Now, what I'm going to show you here, the reasoning why this works, this isn't ever anything you would probably show students, but it is important for you to understand it, why these things work, why these rules work the way that they do. And so for this particular one, I'm going to come way back to one of these strategies we learned for mental calculations involving division. We did this maybe a couple weeks ago. And it was the technique called equal quotients. And if you recall, if you were going to divide something like 80 divided by 16, one of the ways you could do that in your head was to divide them both by the same thing, change it to smaller numbers, and then that one might be a little bit easier. And maybe you know that 40 divided by 8 is 5, which means 80 divided by 16 is also 5. So by dividing by an equal quotient, you can make it into an easier problem to do. This also works by multiplying by some equal number. And so that's the technique we're actually going to use here. So let me show you, again, a visual that goes along with this. So here is the problem, 1/2 divided by 1/3. Now, we would learn these days to multiply 1/2 times the reciprocal of 1/3, or inverted 3/1. Multiplying across, we get 3/2, or 1.5. But here's what that looks like if we apply that equal quotients principle. This might take you a few minutes to just sit and stare at and think about. If we start with 1/3 here, and we start with 1/2, and we triple both of the amounts, meaning I'm going to multiply both of them by 3, just kind of like we divided both of them by 2. You can also multiply by something. What that gives you is 3 halves here and 1 whole here, 3/3, or 1 whole there. Why did we do that? Why would we do such a thing? Let me show you with numbers. here was the original problem, 1/2 divided by 1/3. And what I did was I took 1/2, multiplied it by 3, and then we are dividing, that's just this part, and then we're dividing that by 1/3 times 3. So 1/2 times 3 divided by 1/3 times 3. What happens here? This becomes 3/2, and this becomes 3/3, which is 1. And any number divided by 1 is just itself. And so notice that when we multiply this second fraction by 3, that divisor becomes 1. What happens to our first fraction? When it gets multiplied by 3, it tells us what that eventual answer is. And so this has the same exact effect as just taking and multiplying by the reciprocal of this number. Now that, again, has some, it's a bit complex. It's, again, probably nothing that you would show your students, at least young students first learning these things, but that is why it works. Now, if you want to have some real fun, here is our algebraic explanation of this. And I think this is one of those things that's best for you to just pause and take a look at and see how it relates to what we were just doing. Here's what we're dividing by. Here's our divisor. If we take the reciprocal of that, multiplied by both the first and second fractions, again, we can use that because of that equal quotient technique that we learned before. In this second parenthesis, look what we end up with. CD over CD, which is just 1. In the first parenthesis, we end up with the first fraction, A over B, times the reciprocal of C over D. And that's why we end up able to do that procedure instead of the division. That's why that works. That's why that technique, that algorithm that you learned a long time ago actually works. And so here is how we often define division of fractions. For any fractions, A over B with C over D, A over B divided by C over D is equal to A over B times D over C. And so let's do a little bit of practice as we bring this video to a conclusion. So let's try these 3. I'll go ahead and put these up. You pause the video and then come back. All right, go ahead and pause and try these on your own. I went ahead and started those. So in each case, you're going to be multiplying by that reciprocal. Once it's changed to multiplication, just multiply straight across. 1 times 3, 2 times 1, and then simplify it. 1 and 1/2. For this one, 7 times 5, 8 times 2, and then we need to simplify that. That one's a little trickier. 16 times 2 is 32, which leaves us 3 more over 16. Notice this one was -1/4. When we take the reciprocal, we learned before that the negative can go in either spot. It's generally best to keep that up top. So we'll multiply 2 times -4, 3 times 1, and then we will convert it to that improper fraction, 2 2/3 with a negative out front. Now, the last thing we'll do is just examine mixed numbers as well. And so here is, I'm going to paste this entire slide so you can read this as well. There are multiple ways to do this, but one method of computing the quotient of 2 mixed numbers, like we see here and here, is to replace them with improper fractions. So we change them to improper fractions and then use that definition that we just talked about. So why don't you try both of those? Convert these to improper fractions, then do the process of division. One thing that I've noticed over time is often we try to do too many things at once. So watch out for this mistake. I'm going to start by changing them to improper. 3 times 5 plus 1. 8 times 1 plus 1. But it is still a division problem. We have to invert and multiply now. So we would do 16 times 8, which is 128, and 3 times 9, which is 27. Change that into a mixed number. 27 times 4 is equal to 108, which leaves leaving us with 20 over 27. For the second one, again, change to improper first. 4 times 8 plus 3, 35 over 4, divided by 2 times 2 plus 1, 5 over 2. Now we change to multiply, and then we invert that second fraction. This gives us 35 times 2, which is 70, 4 times 5, which is 20. There's a nice easy way to simplify those. Divide by 10, knock off those zeros. 7 over 2 simplifies to 3 and 1/2. And so again, division is a little bit trickier to represent visually, but hopefully this gave you some, again, deeper understanding of how both multiplication and division with fractions do work.